Good morning, good afternoon, good evening to all people who are joining the Joint Affect IEEE CSS webinar series on nonlinear control systems. This event is co-organized by two technical committee from the IFAC as well as IEEE. And it is organized by a number of people, Hiroshi Ito, Claudia Califano, Andrea Serrani, and myself. And it is my pleasure today to introduce our next speaker of our webinar series, which will be given by Professor Kirsten Morris from University of Waterloo. Before we start with her talk, I would like to introduce her a bit. So Professor Morris is a professor of in Applied Mathematics departments at the University of Waterloo and a Faculty of Mathematics Research Chair. And she has served various different positions in our community, ranging from Vice President of IEEE CSS, Vice Chair of the SIAM Control and Systems Theory Group, and the Chair as well of the group. And she has written a number of books, including the Control Design for Distributed Parameter Systems, Introductions to Feedback Control, and she was also the editor of the book Control of Flexible Structures. She's also a fellow of IEEE, IFAC, and SIAM, and she has received many honors in recognitions of her accomplishments, including the IEEE CSS Distinguished Member Award. Her research interests are very broad, ranging from control and estimations of systems modeled by partial differential equations, also systems that contains hysteresis that we encountered in many of the smart materials. Her recent research focus on improving performance through attentions on the actuator locations, as well as sensor locations as part of the estimator design. And if you have any questions during the seminar, please feel free to put your questions into the chat box, and towards the end, we will try to look into those questions as well so that Professor Morris can address it. So I think without any further ado, I would like to give the floor to Professor Morris. Professor Morris?
Thank you, Bayu and Hiroshi, for the nice introduction and the invitation. I have to find the talk now. We had it. I'm sorry, it was here.
So I hope that...
I know we had it up a second ago and then it's gone. Here it is.
Yeah.
Okay. Do you see it?
No, you haven't shared it yet.
Yeah. Hang on.
Yeah, we had it a couple of moments ago.
Yeah, it disappeared. Here it is.
Okay, good.
Okay, there we have it.
Yeah,
full screen.
Full screen. Okay.
Okay, great. Okay, now we can start. So I'm going to talk about some work we've been doing here on partial differential algebraic equations. I want to thank you. This is joint work with some students and postdocs, and also Birgit Jakob, who's in Germany, and Amir Kajapur, who's a professor here. And it's been funded by NSERC, which is our major funding agency. And some of the work I'm talking about at the beginning was funded by GM in Canada. And also we did some of the computing work on a computer that was bought with funds from the CFI organization. Okay, so I'm going to actually start talking about, this was the part of Sepida Afshar's PhD work, and it was funded by GM on looking at estimation in lithium cells, basically state of charge. It's there's quite a few challenges associated with it. I'll talk about some of the results, but actually this led to a lot of open questions, which really led to theory that I'll talk about in the last part of the talk, which is theory of PDAEs and some specific methods for controller design. So just a little bit of a recap for lithium ion cells. they've become really popular. They have a lot of really nice characteristics. They have a very high power and energy density, which means you get a lot of power out of a relatively small battery. And they don't have memory effect, or very minimal memory effect. What's called very low self-discharge. They'll sit for a while. They have a very long life cycle. You know, we put them in cars now that'll last for like 10 years before you need to change it. They're used in, like I said a minute ago, in vehicles and many other applications. And there's some challenges with them. And one of the big challenges is in determining available charge. So it's just a nice graphic here. You really need to know the good charge estimation, because if you know how much charge is there, then we can really use the full capacity of the cells of the battery. And then you lead to like fewer charging cycles. Fewer charging cycles will extend the life of the battery. And it'll also help having better cell energy balance. So you're pulling power out of, you know, cells that have the most charge in them. There are several big challenges. One is that the models are quite complicated, and I'll show you a sort of a really standard model in a minute. And the other challenge is that from a practical point of view, all we can measure at the terminals is either the voltage or the current, and the voltage or the current is only very loosely, very weakly coupled to the actual state of charge. So it's a very challenging estimation problem for several reasons. I'm just going to give a really brief overview. So the main variables are the electric potential and the ion concentration. And then there's a bunch of independent variables. The length along a cell. I'm just going to talk about a single cell. So the length along the cell, the location in a solid particle, which would be R, thinking of it as being spherical, and then of course time. And what it leads to is a coupled set of nonlinear partial differential equations with three independent variables. We're going to get rid of one of them. One simplification that pretty well everyone does is you assume that the particles are all spherical, right? And that you don't consider any number of different radii. We just say n, they're called bins. One bin would be just one. They've all got the same radius. The model I'm going to talk about here is sort of intermediate, and we allow for three different. So here's a 3-bin electrochemical model, due mainly to these two people here, Thorat and Fargonica and Delacourt. So it's complicated. We're not going to all remember it. So C1 is the electrolyte concentration, and the other three are the 3-bin ion concentrations. So these three, the first 4 equations are nonlinear diffusion equations. Okay, there's a lot of parameters, but that's what they are. And then the second two is phi here. Phi is the, and phi 1 and phi 2 is the potential on the two sides, the electric potential. So those are electrical equations. So you have chemical diffusion is the first 4 equations, which is sort of fairly slow. But the electrical dynamics are very fast. So they're in equilibrium. So we have some parabolic equations coupled to an elliptic equation. So this is a system of nonlinear, what we say, partial differential algebraic equations. So the last two in this case are not strictly algebraic because they have derivatives, but there's no time dependence. So this combination of equilibrium and dynamic equations along with the nonlinearities makes them very challenging. There's also some boundary conditions, but I'm not really going to talk about them. In designing the estimator, we first made some simplification. So we already decided on 3 bins. The reaction rate, which is that function IK, was replaced by something a little simpler, which I'm just calling I tilde, slightly simpler, but also smoother. The basic model had a jump in it, so we replaced it by something that was very close in value, but smooth, so it was differentiable. And then C1 here in the 5th equation was replaced by its initial value, which made some other calculations easier. And the other big one was that if you're when you're charging it, you get a current source on the boundary. We replaced that by a local distributed control. So it's now a bounded operator. It's simpler numerically. I'm going to talk about, so the big challenge here, right? When we do, of course, we're going to approximate these PBEs at some point, but there's a big challenge here with the elliptic equations. So what do we do with those? What we did here was, first of all, we can use the implicit function theorem, and if you analyze these equations, it implies a unique solution for the potential in terms of the concentration. So we don't know exactly what that function is, but we know it exists and it's differentiable. So it's got some linear approximation. And then we differentiate with respect to time, which gives us a differential equation for the potential. So people that have worked on DAEs, this kind of corresponds to, we're roughly considering it as having differentiation index 1. We sort of differentiate it once and we get a system of ODEs. What do I want to talk about? This is actually, this is really not the best way to handle this. This is really one of the open problems associated with these equations, is how do we handle the algebraic part? Because we use the implicit function theorem and then a linear approximation, there's an error there. There's an error in differentiating, and then there's an error in solving it at the beginning. So there's several sources of error. So actually, I'm not going to show you the estimator equations, but in the estimator equation, we introduced another, there's the filter, of course, but then there's also another kind of correction term that feeds in the residual from solving these algebraic equations. And it seemed to work okay, but I think that's an ongoing research issue. I had another student look more directly at doing estimation, and if you do the Kalman filter design, like either extended or unscented, if you do it directly on the DAEs as opposed to differentiating them and converting them to ODEs, you get much more accurate estimation, but it's more time consuming. It's more time consuming, but more accurate. So again, there's, I think, some really important work to be done there. Okay, that being said, that's what we did. We differentiated it. And then we compared it to the simulated and actual potential. So we compared our simplified model to the original model, and it was actually pretty good. Charging and discharging, it was, yeah, pretty close. So here's the issue with the measurements, is the state of charge, right, is determined by the ion concentration, okay? So really what we'd like to know is the ion concentration, but we can't measure the ion concentration inside for sure, but we can't even measure it at the electrodes. What we do measure is the electropotential at the electrodes. It's a battery. And again, there's some open questions here, but the observability with some similar linearized models has shown that the observability matrix, the Kalman observability matrix, has full column rank. So technically it's observable, but it's got a very high condition number. So what's going on with the nonlinear system is a little suspect, but for sure it's very close to unobservable. And that's actually typical for PDE models. We have a diffusion model, and diffusion models are typically only a sort of the best you can hope for is approximate observability. But this is actually even worse than this aspect, is that the potential actually varies very, very weakly with the charge until you have really emptied it out. And because of this difficulty, I mentioned why it's important, because of this difficulty in knowing the accurate state of charge, is what happens in practice is, in order to be on the sort of the safe side, is the cell will only get used maybe three quarters or a half or whatever of what you have, to make sure that there's still some charge left and you're not draining it. Okay, so this was an idea that Sepik Afshar had, was the other way of estimating charge is there's something called Coulomb counting. And Coulomb counting is exactly what it sounds like, is you keep track of the current coming out of the cell and you integrate it, and that should tell you exactly how many coulombs left. And if you know how many coulombs are there to start with, then you know the total charge, right? So, so there's sort of a complicated formula on this page, but that's what it is. Okay, so you just count how many coulombs have left or come in. The problem is it's open loop, so it's not an accurate measurement of the charge. So that's why we like to use voltage, because voltage is actually, the potential is actually directly measuring what's there at the current time. So what we did in our estimator was actually we combined them. So we have the actual potential measurement, and that's combined with the coulomb count. So the two of them can kind of help each other. So this gets us to, now we're sort of ready. This is actually all the hard part. Now we're ready to do the observer design. So the PDEs were approximated with linear finite elements, which is reasonable because they're diffusion equations, right? Linear finite elements are fine. We used an extended Kalman filter, which was updated adaptively. We used some data from a group in France, from the Laboratoire de Radioactivité. And they very kindly allowed us to use their data to compare with our simulation. So we did running a sort of an experiment. They ran an experiment. The real experiment took 1,100 minutes when we were running to sort of see how well the estimator did at estimating the true state of charge. It ran almost 10 times as fast. So it shows it's actually quite, despite the complexity of the model we used, it's actually quite an accurate estimator. So anyway, here's the error. So the surface state of charge is what's on the edge. The really important one is actually the blue line, the bulk state of charge, which is sort of the average over the cell. And this is the error. We're showing the error here. So the bulk error is less than 4%, and even the surface state of charge at worst is around 10%. So we had pretty good accuracy on that. So we're pretty pleased with the results, despite all the approximations we had to do along the way. So as I said, this was work for a company who had zero interest in these theoretical questions of how accurate was the solution to the algebraic equations, what about stability, these questions of how observable is a system for sure, but it was really worth it because it raised a whole pile of theoretical questions that we've been working on for the last, I guess, maybe 4 years. So one of them is extended Kalman filtering. It's been around for a long time, decades, widely used. We know it's locally stable, and there are some theoretical results for stability of extended Kalman filtering for ODEs, but they all assume that the linearizations are uniformly observable. Okay, and we don't have uniformly observed. In fact, you practically, as I sort of mentioned a minute ago, for PDEs, even a regular PDE, you very rarely have what's called exact observability. So there's no way when you're linearizing things, you're going to have uniform observability. So yeah, no results for PDEs, no results for systems that fail to be uniformly observable. Also very little systems theory for PDAEs, right? By now, people have been working on infinite dimensional systems for some time, and the systems theory for particularly linear PDEs is fairly complete. For PDAEs, lots of open questions. In fact, DAEs still is something people are working on, just straight when you have an ODE coupled to an algebraic equation. And having controller and estimator design methods that work directly, use the algebraic equations directly, are really important for these classes of systems because they'll enable us to do controller design and estimator design that's more efficient, but also more accurate, right? We want to avoid doing these kinds of derivative kinds of calculations in particular, or really introduce a lot of errors. Okay, so the first thing I'm going to talk about here is a stability result for extended Kalman filtering. So if you look at, so what is extended Kalman filtering? It's, for PDEs, it's the same. It looks pretty much the same as if we had ODEs. You have a differential equation, and I've linearized it And we assume that the nonlinearity is nice, okay? Uniformly Frechet differentiable. And then there's some noise coming in, of course. And then I have measurements. So measurement Y, which is CZ plus some disturbances. Okay. And then the observer is essentially a time varying observer. So it's the dynamic, again, as any other observer. We have the dynamics, a copy of the dynamics, plus a filter times the difference, the error between the actual measurement and the predicted measurement. Okay. So this is sort of estimators in a way, there's sort of a feedback of the error. So what we want here, we're not actually at the moment trying for any kind of optimal estimation, but we do want to have the aerodynamics to be at least locally stable. So the first issue was to ensure that the Kalman filter that we're calculating at each step, that problem is somehow well posed. So this was some work with, again, Afshar, but also another grad student, Fabian Germ, who's now in Austria. So we have an evolution operator generated by this time varying operator, and then it's coupled to, this is sort of the feedback, the filtered dynamics, first equation here. And then the second equation is the integral form of the Riccati equation. Okay, and then these two equations are coupled to the estimator equation through the filter definition, right? So the usual Kalman filter definition. What did I want to say about this? Usually we see Riccati equations as differential Riccati equations. These are integral form. It turned out to be much more tractable to set the problem up with their integral form because, okay, now I don't have derivatives, I have integrals, which are much nicer behaved. And we were able to show that this coupled system had a solution, and the solution was unique and continuous. So that works out. Okay, so the problem has an answer. The really important part here is if we take the system, it's been linearized, okay? If the linearized perturbed system is uniformly detectable and uniformly stabilizable. So we've weakened, right? We're not asking for any kind of observability. We're just asking for detectability. And roughly speaking, what I mean by uniform detectability here is the same as what we ask for when we're doing approximations, is that there's a sequence of bounded filters. The norm of the filter is bounded uniformly that will give us a stable dynamics. So there's some kind of sequence of F, so A minus FC is stable. And the same thing for the uniformly stabilizable. Okay. So providing we have that, then the filter equation we get generates a uniformly bounded evolution operator. So it's not going to blow up, which is nice. The second part is, what about stability of the aerodynamics? Okay, so we define here an extra term. What is this extra term? This extra term is the higher order terms, right? Phi is the nonlinearity, and then you subtract off the linearization, right? The value of the nonlinearity at ZE minus the derivative at ZE times Z minus ZE. So it's the higher order terms, okay? If there is some M, basically, so that if they're not too far away, the two states are not too far away, then it's bounded above by something to the power M. Okay, so what kind of functions satisfy that? Okay, if it was a C2 function, that would work fine, because then from Taylor's remainder theorem, I could put M being 2 there. But we've made it a little weaker. M doesn't actually have to be as large as 2. It just has to be bigger than 1. Okay, so some reasonably smooth nonlinearity. Then if there's no disturbances, then it turns out that the aerodynamics are locally stable. If I start not too far off from the initial condition with my estimator, they'll decay to 0, which is the most you can really expect from extended Kalman filtering, is some kind of local result. And I didn't type it in here, but okay, someone's probably thinking, what if there's disturbances, there's noise? Yes, if there's some noise on the system, then The aerodynamics, of course, are not going to go to zero, but they do go down to a small value that's determined by how big the noise is. All right, so that was stability of AKF. Okay, so, oh, and I wanted to say something else about this. I wanted to emphasize again, right, this is actually new even for ODEs because we've dropped the requirement of observability. Okay. So then, as I said, yes, so then I started realizing there wasn't a lot of theory for PDAEs. So we've got a separate line of work looking at systems theories for PDAEs. And now I'm going to switch over to being linear because that's as far as we got. We really don't have anything so far on systems theory for nonlinear PDAEs, but maybe someone listening will look at these linear results and maybe we can try and extend them. Somebody can. Anyway, we're going to write it in general form. So we're going to restrict it down. So I've got my dynamics. So the difference between this and a standard system is what? I've got an E, okay, on the left-hand side. A standard PDE or OD or whatever. I've just got the identity on the left-hand side. And then A is some operator that affects the dynamics. I'm going to allow for two spaces here, and I've set it to be more general, reflexive Banach spaces, but in applications, these are generally going to be Hilbert spaces. So you can just think of them both as being Hilbert spaces. But I'm allowing for two spaces, X is inside Z, to allow for, there are some applications where you end up with what's essentially an unbounded operator on the left-hand side. So A is going to be typically some kind of differential operator. E is bounded a lot, but not all of the time. So then in that case where E also has derivatives in it, then we say that E is bounded from some smaller space X into the bigger space Z. And we think of Z as being the state space. The dynamics in general will evolve on Z. They may live on a smaller space. And then A is has a domain that's contained in the smaller space. And for those of you that are not really familiar with PDE theory, the way we handle it in this sort of framework is the boundary conditions get put into the domain of the operator. So A is allowed, for instance, if it was the heat equation with Neumann boundary conditions, I would say the domain was functions that had two spatial derivatives and the derivative on the boundary was zero, okay? And then the dynamics would evolve on L2. So that's how that would work. So this is general. So the big extension, right, is that we've got an E operator on the left-hand side, which may or may not be bounded, and it may or may not be invertible. A couple of examples. One is, so this is not a PDA. This is a system of PDEs, piezoelectric beam with magnetic effects. So the magnetic permeability is not zero. That's over here. So we get a system of equations. There's an E. I mean, the E here is really not that important. It's a bunch of constants. I could have divided it out. I've got some boundary conditions. But what's interesting is most of these materials, and this is fine. This is well posed. Everything works out fine. It has dynamics that don't grow with time and evolve on L2. All four of them are on L2. But typically, most of these materials, these piezoelectric materials, the magnetic permeability is really, really small. So it's typically taken to zero. So this gives us what's called a quasi-static model. So one of the states becomes trivial, and I'm left with this system of three equations. And you can see two of them are basically a wave equation, okay, for V, which is the stretching of the beam. And the third equation is an electrical equation for the electrical displacement. And you can see there's no time derivative on this side, so it's algebraic. Yep. This is actually a class. This is actually really common, is we have a parabolic equation some kind of diffusion type equation, maybe with some drift, coupled to an elliptic equation, and then some boundary conditions. This comes up a lot. If I took that lithium ion cell model and the electrochemical model and I linearized it, we'd end up with a system of equations that looks like that. Okay, so you have essentially kind of slow dynamics coupled to dynamics that are in equilibrium. And then I have an example here of an equation with an unbounded E. So you can see there's a derivative over here on the left-hand side. So this is a different example. So this wouldn't happen with DAEs, right? So for DAEs, the E, right, will be there because it's got 0 rows. You've got a non-invertible E. This kind of subtle thing only happens when you have PDEs, when you have these sort of differential operators. So there's also some water wave models where you have an unbounded E on the left-hand side. If there was a minus here, this model's soil, some kind of soil dynamics, but this actually makes it more mathematically interesting because it's no longer invertible. So I have an E that's unbounded and also with a non-trivial null space. Okay, so back to my class of systems. So this is a class, right? So I'm restricting myself to linear systems here, but it does model a number of important situations. So the first primary questions are well-posedness, right? Do I have a solution to the equations? Is it unique? Does it depend in some sense on my initial condition? Okay, that's what it means to be well-posed. So I'm going to do a little recap for in a standard system. Okay, so there's an identity on the left-hand side. So z dot equals az. So A here, if it was in, this could be finite dimensions, A would be a matrix, but for PDEs, A will typically be differential operator. We talk about something called a strongly continuous or C0 semigroup. I typed in Hilbert space, but it could be a reflexive Banach space. A semigroup is going to be equal to the identity. T here is got an interpretation of time, right? So at time 0, it's the identity. It's got the semigroup property, which means if I take my state basically from time 0 to time s and then to time t, I get exactly the same answer as if I went directly from time 0 to time t plus s. So that's a semigroup property. And then it's the third property is that it's strongly continuous, is that if I take s of tz down in time with positive time, I recover z, okay, for each z, okay? If A generates a C0 semigroup, then A has an interpretation. It's actually the derivative of the semigroup. And the semigroup is a solution to this differential equation. You can think of it, if I was in finite dimensions and A was a matrix, it's the matrix S, the semigroup is the matrix exponential. So the idea of a C0 semigroup is a direct generalization of matrix exponentials to infinite dimensional substate spaces. There's some differences. One of the differences which appears on this page, on this slide, is that you typically, in fact, you almost always only get what's called strong continuity. For each initial condition Z, S of TZ, the solution will go down to 0, but it might take longer to go down to 0 it will take longer to go down to 0 for certain states than other states. You do not get uniform continuity as you do for a matrix exponential. So just strong continuity. But the important point here is that generation of a C0 semigroup is equivalent to well-posedness of the differential equation. If the operator A generates a C0 semigroup, it means I've got a solution. It's unique. It depends continuously on the initial condition, right? I have the strong continuity assumption. So generation of a C0 semigroup is really critical in well-posedness of PDEs. And there's a very famous theorem called the Hilly-Yasuda theorem, which says that a linear operator is the generator of a C0 semigroup on the space Z if and only if A is closed, with domain being dense in Z. That's not that hard to get generally. But this is the key condition, is that there exist constants m and omega such that for all integers k, positive integers k, and real S bigger than omega, I have this bound on the resolvent. Okay, so the powers of the resolvent are bounded above by m divided by S minus omega to the k. Okay, if you have that, you have a semigroup. If that doesn't hold, you don't have a semigroup, right? It's one of these very rare, necessary, and sufficient conditions that exist. It also, those constants m and omega are actually kind of important. They will tell us actually the growth of the semigroup. So if you can take omega to be negative, you've got an exponentially stable system. All right, so that's a bit of background. So what about PDAEs? Okay, so this is pretty tricky. There's some results around already. Rees and Tischendorf and Trostoff did some sufficient conditions on the resolvent itself. Okay, and then Thaler had an interesting paper even before that, where they looked at splitting the space into the kernel of E, right, and its orthogonal complement, and then similarly the kernel of E adjoint and its complement. I'm going to come back to this idea. And then there's this other concept that appeared in this book. It's a pure math book. It's done on general Banach spaces by these Russians, Severdiuk and Fedorov, in 2003, which my PhD student Alla found in doing her background work. And she ended up focusing on controller design, but this turns out to be really useful for establishing well-posedness. So if you go through this and think about working on reflexive Banach spaces, we actually get some really nice conditions for semigroup generation that extend actually the sort of the Hillier-Cedar theorem and also the Loomer-Phillips theorem, but I'm not going to have, I think, time to talk about that today. So what's going on? So the first part is what's in my resolve. My EA resolvent is the set of all S where S E minus A is a bounded inverse, okay? But I'm also going to define something called right and left E resolvent. So the right resolvent, I multiply the resolvent on the right by E, and the left resolvent, I multiply it on the left by E. Okay, we're going to say, in the original Russian book, they call this weakly radial, but I found that term kind of confusing. So we've essentially we've decided we're going to call this radiality index. So it's a new kind of an index. So we say the system has radiality index 0 if S is in the resolvent for all positive S, and the right resolvent is bounded above by K over S, and similarly, the left resolvent is bounded above. Okay. And I'm only going to talk about radiality index 0 today, just to keep the discussion fairly simple, which for people who have worked on DAEs corresponds to roughly a differentiation index 1. Okay, we'll see this later. But I'd like to point out that this has been extended to the resolvent in some right half plane, but also in a more tricky way to higher index in a paper by Mebet Erbey and Birgit Jakob and myself that's on arXiv. Okay, so but I'm only going to talk about index 0. So the big thing is here is we're going to decompose the space as Thaler did, but we're going to decompose it differently. You look at x0, which is the kernel of the right resolvent, and z0 is the kernel of the left resolvent, and then there's x1, which is the closure of the ranges. Okay. So x0 is actually, in fact, you can show in about 2 lines, it's exactly the kernel of E. Okay. And then z0 is not exactly the kernel of E. What we have then is if the radiality index exists, then those spaces decompose the space. X decomposes into x0 and x1, and Z decomposes into z0 and z1. And we can construct projections onto those spaces. So P is the limit as S applied to the right resolvent, take S out to infinity. And then similarly, Q is the same kind of thing, but on the left resolvent, okay? You can show that they're bounded operators on X and Z respectively. This is the important thing, is that they're actually non-orthogonal projections. So we're doing a projection of the state space. We're splitting the state space, right? And the X0 projection is the same one as Teller and Teller used, but it's not orthogonal, it's non-orthogonal. And that actually turns out to be really important, because by making it non-orthogonal, it means that when I project, the projection is invariant with respect to the domain of A, which for PDEs is really important, because I sort of mentioned an example a minute ago. The domain of A are the functions that I'm allowed really to apply the operator A to. They're functions that smooth enough, that have the right boundary conditions. So if X is in the domain of A, then it turns out that PX is also in the domain of A. And not only that, AP is equal to QA. So there's a sort of a commuting property, and then a similar commuting property on E. EP is equal to QE. And the proof is pretty straightforward, because it's defined, the projections are defined using these right and left resolvents. So that helps us with that gives us the commuting. So that's the key part. So with that splitting of the space, we define E0 to be the restriction of E to X0, similarly A0. E1 is the restriction of E to X1, similarly A1, okay? And again, because of the special way we're splitting the space, if the radiality index exists, then when we do this restriction, they're actually invariant. So A0, which is A restricted to X0, maps onto X0, okay? And E0 maps onto X0, similarly E1 and X1, okay? Not only that, the A0 part turns out to be boundedly invertible, which is actually going to be really helpful. Again, this part here is just a little bit of algebraic calculations. It follows from this commuting property. Okay, so what can we do now? We've split the space, and the splitting of the space gives us a splitting of the operators, which is invariant with respect to the spaces. So it gives us a way of giving what's in DAEs is called a Weierstrass form. So I'm going to use the same word here. So we split the space, right? X gets split into X0 and X1, and Z gets split into Z0 and Z1 with Q. So the two together, I'm put tildes on them. Yeah. Okay. So if the radiality index exists, and now I need another assumption. I need the range of E is closed, which is generally happens. Then I apply these projections basically. So I apply P tilde to one side and Q tilde to the other side. And then I get now, because of the invariance with respect to the spaces, E, when I write E on X0 cross I1, I get an E0 and an E1, and similarly A, I get an A0 and an A1, okay? Now, because I've only got radial degree index 0, E0 turns out to be 0. More generally, if there was a higher index, this would be a nilpotent operator. But here it's 0. But in any case, I'm going to get E1 is invertible. So now I've rewritten the space with the decomposition. The PDAE has this really nice form. So now I can look at it and I can see really exactly what's happening is that Z0 is supposed to be identically 0, right? And then Z1 actually has dynamics. So all the dynamics are on the Z1 space. But now you can see there's an operator here. So there's a question now, right? So are these dynamics on this smaller space, are the dynamics well posed? Okay, so now I need a little bit of an extra assumption. So let's introduce this idea now of E radiality. So it's E radial if S is in the resolvent for all positive S, and there exists a K such that for all integers, positive integers, and all real S, the powers of the right resolvent are bounded above by K over S to the N, and the powers of the left resolvent are similarly bounded. Okay. If E is equal to the identity, then there's two resolvents, of course, are the same, and this inequality is exactly the conditions of the Hilliard-Yasuda theorem. Okay. Clearly, actually, this is a little stronger, right? Any E radial operator has a radiality index, because the definition of a radiality index was exactly this, except N was only 1. Okay. And if I could take K to be 1, then they're actually equivalent, because I could just take powers on both sides. Okay. But in general, the pair of operators could have a radiality index, but not be E radial. Okay. So now we're ready. So if the operator, and maybe we'll shift it to allow for some kind of instabilities, maybe if it's E radial and the range of E is closed, which I needed for that decomposition, then the operator E1 inverse A1 with the domain of A restricted to X1 generates a C0 semigroup on X1 with an exponential bound, and the component on X0 is identically 0. So most of that follows from the previous result from the radiality index, right? That gives us a splitting of the dynamics, and the dynamics on X0 are identically 0. But the additional property of being a radial, okay, when we write it out and simplify things, we end up with exactly, the bound reduces to exactly this, which is precisely what you get in the Hilliard-Yasuda theorem. So we can use the Hilliard-Yasuda theorem to conclude that on the smaller space, we have well-posed dynamics. We have a semigroup evolving on the smaller space. So I think this is sort of an interesting way of looking at it. It's kind of, there's some practicality, because it enables us to establish things like whether or not the dynamics are well posed, but I think it also gives us some insight into what's going on, because once you've did decomposition, you can see that yeah, there's actually a state. If you sort of define the states, there's actually a state that's identically 0, and then another part of the state that's evolving, and sort of, we can think of it as the true state space. The true state space is actually smaller than what we use when we define the original PDAE. That's kind of, I think, one of the ways we can look at it. And then we can also flip the order of the derivatives around, and then we get semigroups on Z. And as I said, all this has been generalized to higher radiality index. It's on arXiv. Oh, as an example of this, so the simplest type would be these coupled systems. So what fits that? This is a very common setup. E here is the identity and some 0. Where do we see that? We see that with the linearized lithium-ion dynamics, and with parabolic elliptical equations, the piezoelectric beam with quasi-static, with the magnetic permeability 0. Those are all examples of this kind of system. So in here, we've got decoupling into 4 separate operators, okay? Yeah, a bunch of examples that fit this. Provided that, the key thing is, provided that, I'm gonna go back here. The key assumption is that A4 here needs to be invertible, okay? If that's invertible, then everything works out really nicely. So if A4 has a bounded inverse, and there's some nice properties with the domains, and A1 generates a semigroup, which makes sense because that's the dynamic part. It should generate a semigroup without the algebraic variables. Then we can use these results that I just showed you to say that the dynamics of the system are well posed and they evolve on X1. And here the projection actually looks like this, right? So what we have is actually, there's a variable W minus A inverse A4 inverse A3, which is identically 0. So there's sort of another, if you redefine the state variables, you'd get one that was identically 0. Okay, so that's some recent results. How am I doing? Oh, I have a few minutes. Some recent results on systems theory. I'm going to talk really briefly a little bit about direct controller design. Okay, so just looking at a parabolic elliptic system. So this is in one space dimension. So I have a basic diffusion equation here, and then a steady state one here. So a slow one and a fast one. And then I'm applying control at the boundary, Norman control at the boundary. And provided that gamma is not equal to one of these integer multiples of pi squared, everything, it'll fit what I just talked about. It'll be well posed. And the growth rate of the associated semigroup is minus rho plus alpha beta. So this is interesting. When we first calculated, I was a little bit surprised. So this is one of the interesting things about coupling systems is this equation here, which is a diffusion equation. This can be stable. Supposing this is stable, okay? So rho is 0 or positive. And then I'm coupling it to an elliptic equation, which is in equilibrium. So it's like extremely stable, okay? But the coupling can destabilize the system, right? If the coupling is really large here, you can take a stable system and the coupling renders it unstable. So it kind of more motivation for studying these systems. So what Ella looked at was doing backstepping. So I'm going to do a little bit of overview on backstepping. So what could we do here, right? We could transform the system to Weierstrass form and then find a transformation on that. But we've been trying to like do kind of procedures that we can generalize to more complicated ones. We didn't really want to do that. We wanted to sort of study it, knowing it's well posed, but try and do the controller design without the transformation. We could find a double transformation, so do like a vector value transformation. We could also just try and transform only W, because I've only got one control here, right? I've got two equations and only one control. So what she looked at was like, let's just do only W. So what you do in backstepping, this is a general backstepping thing, is you define a transformation. So W tilde is my new variable, okay? And I do a Volterra transformation. And the nice thing about this Volterra is I know it's invertible. So I've got a transformation that's guaranteed invertible. And this particular one was studied. This is the advantage of this one. We took a known transformation and tried to show that it worked. The advantage is that Kirsten and Smelnyev already studied it. They showed that this equation had a solution. We also have an expression for the inverse. So there was a lot of groundwork that was already done. So yeah, so let's try that one. That transforms it into this similar system, okay? And this is the thing with what happens in backstepping. So W tilde is equal to, by definition, is equal to this, W minus the integral. So then if I differentiate both sides, I get this, right? So I get an extra term because I have to differentiate the integral. And then I evaluate at 1, right? So that's what it's equal to at 1, okay? But I know that the original variable, the derivative at 1 is the control variable. So I can substitute that in. So now this tells me what the control variable is. So if I know what my transformation, my kernel K is, it gives me an exact closed form representation for the control signal without any approximation. So that's the thing that's very attractive about backstepping. So Ella showed here that in fact, even though we're using just one control and only one transformation, that for certain values, it's exponentially stable. And then by analyzing it slightly differently, we got better results. So these are sufficient results. They're not tight, but they do show that there's some advantages there's some power to just working with the one transformation. And here's the results, right? So this is an unstable system. The original system was stable, but the coupled system is unstable. And then with the control signal, you can see it decays nicely to 0. Let me see the control signal. And I've just got one slide on this. We've also done just fairly recently just looking at index 0 linear quadratic control. The only extra assumption is that the state weight decomposes. And the idea here is we want to make sure the control is consistent with the initial condition to avoid distributions due to this algebraic part. It turns out that there is an optimal one, and it can be found by solving a differential kind of Riccati kind of an equation coupled with an algebraic equation. And the nice thing is, to solve these equations, we don't need to compute the projections. We needed the projections for the proofs. We need to know they exist, but we don't need to actually construct them to calculate a control. So that's my, I think I'm out of time. So I'm hoping I've introduced interested people a little bit in PDAEs. They come up in a lot of applications. We have some results that extend Hilliard and also Loomer-Phillips, which I didn't talk about. So, but there's a lot of open questions still for well-posedness, even for linear systems, establishing systems, practical ways of ensuring that we have well-posedness, and then what kind of bound we have on the solution. For nonlinear, it's pretty open. We've done a little bit of work on backstepping, so some backstepping transformations. There's some linear quadratic control results. And I also like to mention that Timo Rees in Germany has also got some results using a slightly different approach and some different assumptions on linear quadratic control. But the idea here is, right, we're working directly with the PDAs. We're not trying to convert them. But more synthesis methods are needed, and estimator design is also lots of problems there. So, thank you, everybody.
So thank you, Kirsten, for a very insightful presentations and lecture. I saw that there was questions, but then the questions was somewhat removed. So if you have any questions, maybe you can turn on your microphone, and then you can
Yes, I have a question. My name is Kamen Perez, and I have a question regarding the nonlinear system, the nonlinearity. You said that a necessary condition to derive your results is that the function, the nonlinear function or operator, is Fréchet differentiable. Or
let me go back. Should I go back to the slide?
Yeah, somewhere around 20.
Oh, good. You wrote it down. Thanks. I'll go back to that. Oh, here.
The function phi, the function phi.
Yeah.
What will happen if this function is not differentiable? Let's say it's a Rayleigh function or hysteresis function, sort of.
Yeah, that's a good question. So what actually needs to be differentiable? So R being differentiable, the one that you solve for being differentiable, is a consequence of the implicit function theorem. But what needs to be differentiable is the algebraic equations.
There was a function phi.
Yeah, so phi is the potential, R is the function we solve for. So what needs to be the implicit function theorem, it generalizes from basic calculus on Rn up to function spaces, but the differentiability of the equations, the functions in the equations at the top of the page, you need to use those to use the implicit function theorem to solve for it. It's same as the inverse function theorem. It's just a similar result. And then you get R is differentiable, you get that for free.
I think you're talking about Taylor series linearization at some point.
Yeah, actually, no, you can find it somewhere. So yeah, it's a good point. So the fact that phi is locally a function of C is exact. That's true. It's a differentiable function of C locally. Can you write it down? That's hard. Okay. So
no,
it's an exact result. It's an exact result. But what you have to do from a practical point of view is you end up working with the linearization, which is why from a practical point of view, it's not great.
my
Yeah.
suggestion is, can
Yeah.
you use some kind of approximation different than Taylor series approximation in terms, let's say, if hyperbolic tangent functions or sort of, depending on the nonlinearity you have.
Yeah. Yeah, I don't know, maybe. Yeah. Like I said, we were trying to get something to work here. I'm not claiming this is the best way to get it to work.
Okay.
I think really
Actually,
staying
this
with the
is
algebraic form is the best
So-
thing, not to differentiate. Yeah.
okay.
Yeah.
Okay, so
Okay,
come
thank
on, due to time, I was wondering whether there are other questions
Yeah.
from others. Feel free to turn on your microphone.
I think
As-
our, yeah.
Can I go with one
Yeah,
question?
Arijit. Yeah, go ahead, Arijit.
Thanks, Kirsten, for this nice talk. And I was just wondering about when you're talking about PDAs and you're mapping from X to Z with the E operator. And then probably at some point of time in the archive file you're talking about, you also talked about an example where you operating from Z of xt to another space. I got confused. The Z is just a member of this capital Z or the calligraphic Z space, or it's just a function of the position and time.
Oh, you want an example where X and Z are different? The spaces?
Yeah.
Yeah, because I said here there's the two spaces. Is this what you're asking me about?
Yeah, I was a bit confused about.
Yeah, so that's kind of why I put, okay, so here's an example where they're different. So this is the A operator here, okay?
Yeah.
And it's, yeah, so it's got a domain, right? So enough derivatives and the right boundary conditions. But on the left-hand side, I've also got a derivative, right? So this, I can only apply this to functions that have two derivatives. So I define the space, and also it's got boundary conditions. So I have a space X that has functions that have two derivatives, and then it gets mapped into functions that are just squared integral. So here's a case where X is inside Z. So the E here maps functions with two derivatives to functions that are just square integrable. Yeah.
So Z is basically an extended space of the actual state space in a way, but there is no physical interpretation per se, I would say.
Yeah, more commonly Z would be the L2 here would be the state space. That's but the result actually you can flip it around a little bit. Yeah.
Okay.
Yeah.
Okay, so I think due to time, I would like to thank again to Kirsten.
Okay, I have another question.
Come
this
on,
is
a very, very short one.
okay, it's very short. You're talking about generalized state space description here, right? Where A, B, C have derivatives inside. Can you relate this to the regular type of systems like singular systems for algebraic differential equations?
Yeah, so it's actually a generalization of that idea, right? E is in general not invertible, right? It's a singular system.
Okay.
Yeah, so we're looking at these, but on infinite dimensional spaces, not just on our end.
So you relate all these results to partial differential equations, right?
Yeah.
Okay, thanks.
This is already a result quite many decades ago. I still remember this. My PhD. Okay, so I would like to thank again Kirsten for a very nice lecture. And for the next lecture, we will announce it in our website of our TC on nonlinear control systems of IFAC. So please take a look on that. And I would like to thank you all and see you very soon.
Okay, thank you.
Thank you.
Thank you, Kristen. I enjoyed the talk very much, and I had question, but I will ask question later. Thank you very much.
Bye.
Thank you.
Yeah, thank you.